Here you are, Franek.
Okay, can you see my screen?
Yes.
All right. Well, welcome everyone. My name is Franek Hasiuk, and I'm going to present to you this short introduction to a rapidly growing field in the petroleum industry known as carbon capture, utilization, and storage. You may have heard about this family of technologies and business processes and tools before, but what I'd like to do is sort of lay it out to you in a logical fashion, talking about each of these steps, the capture, the utilization, and the storage in a manner that can sort of give you a fuller picture of what this group of technologies means. All right, just in summary, to get things started here.
Franek, excuse me.
Yes.
I think you don't have your screen.
Really? Okay.
Yes. Can you share? Yes. Now we have.
Now you have it.
Yes.
Huh. Okay, there we go.
Excellent. Excellent. Thanks.
Let me see. Yep, there we go. So just as a way of starting here, I wanted to lay out some bigger ideas here. And one of the bigger ideas is that the petroleum industry is changing into a carbon industry as we start to think more holistically about not just bringing oil and natural gas to the surface of the earth, but also what happens to those carbon atoms once they've been combusted in some way, or they've weathered in a landfill or something like that and become CO2. And so CCUS is a shorthand for the technologies ultimately that keep CO2 out of the atmosphere, because we've known for a long time that carbon in the atmosphere contributes negatively toward the health of our climate. And so by doing these CCUS technologies, we can first and foremost keep CO2 out of the atmosphere. On the plus side, we can start thinking about that CO2 as not just a waste, but as some sort of a valuable product. There's many examples through history of people taking the waste stream from one industry and turning it into the feedstock for another. Ultimately that waste is free, and if you can even do a little something with that waste, you can essentially make infinite profit since your costs are minimal. Now, CCUS technologies have implications for the upstream, midstream, and downstream parts of the petroleum industry. And through CCUS, we can deal with a problem, that problem of CO2, with a lot of the skills and tools we already have. So it's pretty exciting. Now, we all know CO2, like maybe if you don't think about those two letters in the number very often, with every breath we take, right? We are breathing in oxygen and carbon dioxide that's in the atmosphere, right? Along with nitrogen and argon and some other fun stuff. But our lungs are, conversion cells for turning that atmospheric gas into a respiration product, right? So we take gas in that's, 4/10 or 4/100ths of a percent CO2, and we turn it into 4% CO2. So with every breath you're taking during this entire presentation, you're making CO2, right? So I want you to sort of like think about how, this isn't just some nebulous process that's just happening in a big power plant when we burn fossil fuels and make CO2. But really making CO2 is part of what life does on this planet, and it's intimately associated with the carbon cycle on this planet. Even if you maybe weren't familiar or thinking deeply about how you yourself are producing CO2, you certainly may have had some CO2 today in your diet, right? A lot of fizzy drinks out there are fun, enjoyable to drink, especially, some of these things like Coca-Cola or Fanta. If you don't like that much sugar with your CO2, you might do something like Perrier or LaCroix. Or have club soda or tonic water. You may even have one of these fancy machines that carbonates your water on demand to give it that extra little pep. So here, here's an example of, an industry you might not think of that's a CO2 user. And in fact, beverage grade CO2 is rather an expensive commodity, and it's always something looking for, a way to find a lower cost source of CO2. So certainly this is an industry that's looking for more CO2 or cheaper CO2. And if that's something that the petroleum industry or the carbon industry can do, then that's a new market. Now, you yourself may also have emitted some CO2, not just through respiration, but we've all experienced this sensation after having a rather fizzy drink. And I just wanted to start us off on a good note here, so that we can think of all the ways that CO2 might be a part of just our own daily lives, not necessarily just these sort of more abstract geological concepts, engineering concepts, or business processes. Okay. So then from there, I think it's helpful to learn some new words, or at least more explicitly define some of the words we're going to talk about in this presentation. And so first of all, carbon dioxide, I've mentioned it a few times, I've shown you the chemical formula for it, but it's this colorless, odorless gas emitted by burning or respiration. 1 carbon, 2 oxygens, a very simple molecule. Now, carbon sequestration was a term that was developed to talk about not emitting CO2 into the atmosphere. So there are a lot of industrial processes and transportation processes that involve, the emissions of CO2 from, the combustion of hydrocarbons. Now, if we sequester that carbon, if we take it from the source of combustion and turn it into a solid, or bury it as a gas or supercritical fluid in the subsurface, then we've sequestered it, we've kept it out of the atmosphere. Now, that term carbon sequestration sort of morphed into a term CCS, carbon capture and storage. And this was sort of an evolution talking about, well, it's not just the sequestration that's important to think about. We also have to think about capture. How do we actually capture that CO2? And that engineering challenge has taken, the whole idea of carbon sequestration to the next level, because some of these capture facilities that go on the side of power plants, these can cost hundreds of millions of dollars to develop and operate. And so it's not a trivial act to capture CO2. And so having that as part of this acronym has been really important to develop, the holistic thinking about, what goes into a carbon economy. Now, from CCS, then, another letter started getting added to the acronym. I think this may be the last one, but certainly here's one that is important to understand, and that's by adding the U for utilization. And so this acknowledged the fact that, well, it's not just about capturing and storing underground, it's, coming up with new methods and new business processes to use CO2. Whether this is in strengthening concrete, whether it's in the beverage industry or the dry cleaning industry, but finding new ways to use CO2 so that it's not just about capturing it and storing it away from, the economy forever, right? So CCUS is the acronym I'm going to use a lot in this presentation: carbon capture, utilization, and storage. Now, another acronym here, CO2-EOR. So this is actually a utilization. This is using CO2 to enhance oil recovery in an existing oil field. Now, this also has some, bleed over into storage, because a lot of that CO2 will stay down there in the reservoir. But CO2-EOR is the acronym I'm going to use when I talk about, injecting CO2 into an oil field to enhance production. We might mention carbon neutrality, or you may have heard about carbon neutrality. And so this is making some sort of a process neutral with respect to CO2 emissions to the atmosphere. This is usually either through sequestering the produced CO2 or through not producing the CO2 in the first place. And you'll hear in the news a lot of discussion about, companies making pledges to be carbon neutral. And that's usually not through completely eliminating the emissions from their business line. It's through offsetting. And so that's the last term I have here, carbon offsets. That's achieving carbon neutrality through interaction with some other party. So maybe, your company is a power plant and you emit a certain amount of CO2. Well, you pay some landowner to grow trees on their property, and those trees will pull carbon out of the atmosphere and sequester it as biomass. And so, from an accounting standpoint, your carbon emission is offset by this carbon sequestration or carbon storage at this other entity. You may have seen it when you've, when we used to travel by airplane a lot. I remember seeing on the airplane websites, you could buy what was called a carbon offset for your flight, which would offset the carbon emitted by your travel on that airplane. Okay, so news. Let's talk about news with respect to CO2. A lot of things have been happening with respect to different countries, different sub-national entities like states. We call them states here in the United States, but even cities are getting on board with laying out new rules for carbon emissions. One of the big sort of themes that's been coming out lately is that different countries are starting to enact bans on the sale of diesel and gasoline cars going forward. And this is an attempt to deal with the carbon emissions that come from transportation. Now, transportation's a really tricky thing to decarbonize because you can't economically capture the CO2 from a car or from a truck. And so this is the way that these small carbon emitters are being forced by national entities, by governments, out of the carbon combustion business. And this is something that could spread to other industries if they don't come up with ways to deal with that CO2. Now, what's more advantageous for larger point sources like power plants, chemical plants, cement plants, is that they are large single emitters, and so the technology to capture that carbon is a lot easier to do at larger scales. So what is this new CO2 economy or this carbon economy going to be based on? Well, like I said, it's based first on the scientific evidence for global warming from anthropogenic CO2. So that's CO2 that people have emitted is causing the climate to warm, and that's established science. From that, social pressure has urged businesses and governments to reduce CO2 emissions. And from that social pressure, we now have government regulations, like I showed you in the previous slide, that are reducing CO2 emissions, either through fuel economy standards or through the blanket ban on combustion engined vehicles. On the flip side of that, governments are also funding a lot of carbon capture, utilization, and storage research. And that research is helping develop the new technologies, the new chemistries, the new geological concepts that can make different processes, different chemical engineering processes or business processes less carbon intensive, so they produce less carbon, or to come up with strategies for how to keep the carbon that something produces out of the atmosphere. Here in the United States, there are tax credits also that have been enacted that essentially put a price on storing CO2. So if you can sequester a ton of CO2 in an EOR operation, you get $35 a ton as a tax credit. If you do that in a saline aquifer where there's no oil and gas produced, you get $50 a ton. Places like California have enacted what they call the low carbon fuel standard, in which case you can get anywhere between $65 and $200 per ton for sequestering CO2 out of the atmosphere. And these are very attractive, and they're causing real private sector investments in carbon capture, utilization, and storage, because now there is an economic driver. And we see a lot of times that when we can kickstart these industries, then that industry can take over and really figure out how to do things efficiently with respect to the goals that we need to achieve. Okay, so CO2 in the atmosphere. I wanted to show this plot. It's a pretty famous plot that shows both the increase in CO2 concentrations in the atmosphere from 1700 to today, or at least till the year 2000. It's pretty much gone on since then in about the same way. But this shows that CO2 concentrations have increased in the atmosphere since the 1700s when we started the Industrial Revolution and the mass burning of fossil fuels across the world. But what's really important to notice also is that this ratio of the two isotopes of carbon, carbon-13 to carbon-12, has declined over this time. And what that means is that the composition of the carbon in the atmosphere is becoming more and more negative in this carbon-13 to carbon-12 ratio. And what that signifies is that, yes, the carbon that is going into the atmosphere is coming from something with a very negative carbon-13 value, and that is the hallmark of fossil fuels. Fossil fuels have a very negative, as it says here, the delta 13C value right here on the y-axis in pink. But the important thing here is to show that this increase in CO2 isn't coming from natural sources. It's coming from combustion of fossil fuels. Now, you may say like, well, okay, well, what can we do as a world to combat changes in CO2? Well, we've done something similar to this before, and in the 80s and 90s, it came to be realized that there was a hole developing in the protective ozone layer around the Earth, and governments from around the world came together and banned the chemicals that caused that ozone hole. And so the class of refrigerants that were contributing to this hole were banned. And since then, we've seen the ozone hole shrink, and it's currently projected to be almost completely healed within the next 100 years. So it's a really big example of how when we have problems with our atmospheric chemistry, not only can they be solved, but we can actually get the leaders from around the world to come together and agree on something. Recently, there is actually a spike in these ozone-destroying chemicals that was detected in the atmosphere, and scientists from around the world were able to pinpoint where that was coming from, and the local government went in and addressed that issue through environmental regulations on those emitters. But this is a real positive thing, and it shows that we can, our economy can survive when we make these changes. Now, more recently, with respect to CO2, CO2 is a much harder problem to deal with than even, the ozone hole. The ozone hole represented a clear, present, and almost immediate threat to the life of people on Earth. So, governments came together, and the industry that was using those chemicals was not, not a very significant industry. So it's easier to encourage them to use other refrigerants. Now, with CO2, it's harder because we all know how intertwined the combustion of fossil fuels is with our daily lives and with the economies of almost every country on this Earth. And so it's taken a lot longer, and the ride has been bumpier. But recently, we came up with this thing called the Paris Climate Agreement, which sets out a framework for dealing with CO2 emissions and bringing atmospheric carbon levels, carbon growth to a standstill so that we don't see any more negative effects. Now, we shouldn't expect this to be easy. This is something that's really hard, and it's taken a lot of time and political will to get done. But we are seeing as a globe this happening. And what's really exciting is that this brings this new world of carbon capture, utilization, and storage to the forefront in the oil and gas industry. And it's sort of the frontier now. This is where the new opportunities are, and this is where things are going to change in oil and gas in the next 10 to 20 years. So I just want to take a minor break here and just issue a challenge to everyone watching here and listening, and that is that we have the tools as oil industry professionals to contribute a lot toward this goal of decarbonizing the atmosphere, right? We know about subsurface reservoirs. We know about the transportation of gases long distance. We know about international business relationships that are needed to move these materials around economically. And so I think personally, this is a really exciting time in the oil and gas industry, because now we have this whole new concept. And with that concept is going to come some challenges, but it also is going to present a lot of opportunities for new companies to be founded and grow and develop new business models that can help solve this big global problem. So more than anything, you know, I hope that this is a little bit of excitement and a little bit of positivity for the oil and gas industry right now, which you know, has been going through a rough time this year in 2020 with the dramatic drop in demand for oil and gas. All right, so the outline of the remainder of this presentation is going to be, I'm going to walk through these different aspects of CCUS, and we'll talk about storage, transport, a little bit on capture and utilization. This figure here is a very basic figure just showing you know, CO2 capture or separation from a plant. You know, it could be coming from a cement plant, a power station, from elsewhere, getting compressed, transported, and then injected somewhere geologically. So it almost runs backwards to your normal idea of the oil and gas business, where the resource comes out of the well and goes towards some sort of facility, engineering, processing facility. But in this case, it's probably more akin to, say, a natural gas storage field, where the natural gas is being stored in an aquifer in the subsurface. And so we do have those models. We do have that experience as an industry, transporting gases long distance and injecting them into aquifers, or injecting them into subsurface reservoirs, I should say. In the case of CO2, there's no interest in injecting it into a current source of drinking water, or really any water that could be used for drinking. This is only in water-bearing formations where the water has no drinking water potential. Okay, so physics of CO2. During this presentation, I have talked about CO2. You may be thinking of it as a gas, but in terms of transporting it and injecting it, it's often thought of as being transported in a supercritical state. So at a relatively higher temperature and a higher pressure, so that it occupies much less volume. And this is, you know, you've probably heard about transporting natural gas in a liquefied state. You know, this happens through, you know, containerized shipping and things like that. But in this case, CO2 being transported in this denser state just allows, you know, the economics to be more attractive, and it allows you to put more carbon, say, into every, you know, square meter of pore space that you have in a reservoir. That being said, CO2 storage, and I'm going to start here at the storage end of things, because I think that's where a lot of us have most of our experience with respect to this whole CCUS world. CO2 storage relies on a lot of the same system elements that we use in oil and gas. So here's a diagram that shows your typical petroleum system elements that we might call them. So there's trap, and there's seal, there's reservoir, there's a source rock, there's migration routes. For CO2 storage, we need pretty much all the same things. We need a trap that provides that three-dimensional storage volume for that resource. We need a seal, so we need an impermeable formation that keeps the CO2 that's in its supercritical state, keeps it in the reservoir. So you need this porous and permeable reservoir, right? The porosity gives you the storage space, the permeability gives you the injection rates that make it sustainable. You know, you don't need a source rock. We're not looking for, you know, that source rock. So that's one thing to remove from the system. And in terms of migration routes, really here you're looking for the absence of a migration route. You don't want faults that pierce the top seal and would allow either the CO2 or the brine to migrate upwards into shallower strata, perhaps sources of drinking water in the shallower strata. But you also don't want the material migrating down section into the basement, where there might be issues with inducing seismicity, as has been observed with more recent wastewater injection into the subsurface in many places. So finally, I also add the thing here, time. And time is a really interesting aspect of carbon storage, because the chemical reactions that happen as CO2 is injected, right? CO2 itself in a supercritical state is, at its boundaries between the brine and the CO2 undergoing chemical reactions, and that can alter the framework of the reservoir, but it can also cause precipitation in the framework of the reservoir. And so that time aspect of how fast injection is happening and how long the CO2 is going to stay there, whether this reservoir is for short-term storage or sort of ultimate geological storage where no one's going to use this material anymore. Ideally, you would have a situation where all of that injected CO2 would then precipitate out as a mineral and become sequestered for perpetuity. But it's that time aspect that I think that is probably the least understood at this point in time with respect to CO2 storage, but it's the place where there could be a lot of uplift if we can figure out these chemical reactions that really can sequester CO2 into a mineral form. Because again, then we're not dealing with the plume anymore, we're dealing with solid minerals, and solid minerals are much harder to move around with pressure changes than, say, a plume of CO2. Here in the US, the Environmental Protection Agency at the federal level regulates CO2 injection in almost every state in the country. There are 2 states that have applied for and received what's called primacy, or the ability for state level environmental regulators to issue permits for these injection wells. But these permits are quite lengthy processes to obtain, and so it can take year, 2 year, 3 years of very meticulous reservoir characterization and modeling to be able to produce a document that will win you one of these permits. And so it includes very intense site characterization in terms of the reservoir and seal, generally requiring a characterization well and core sample recovery. It also requires characterizing any underground sources of drinking water that exist above the reservoir that could be impacted by this injection. There's strict well construction guidelines to ensure that the materials used in the well for both injection and monitoring are going to be strong enough to withstand the chemical conditions of CO2 injection. There are rules on rates and amounts of CO2 that can be injected. There needs to be a plan for comprehensive monitoring, at least during injection and after injection, and often if you can include pre-injection monitoring, that can go a long way towards showing that you haven't impacted the local environment through the injection of the CO2. There's financial responsibility requirements for who is paying for everything and who carries insurance for these operations. And then finally, there's very strict rules about reporting and record keeping. And so because you're probably saying, well, wow, that's a lot of guidelines, and it seems like it takes a long time for these permits to be issued. Well, part of it is that this is a relatively new type of well, or a new type of process. And so there's not a long history of knowing what you need to know in this case. And so at least in the United States, the regulators have erred on the side of caution to say, well, we want as much information as possible. But as time goes on, I think it's legitimate to expect that these rules to become simpler as we know more what we need to know about these injection wells. There's probably some things we do now that we don't need to do, and there may be things that we don't do that we find that would be important. But right now, because of the relatively few number of these wells that exist and the lack of a long service record, as well as an industry that can help guide these regulations, because we don't have those, currently the regulations are quite strict. I show a little figure here from the Kansas Geological Survey's Class 6 permit that shows a modeled plume extent within the area around a proposed injection well. All right, so like I said before, The two main ways that you would sequester CO2, or the two main processes, would be one through enhanced oil recovery. And so this would be injecting water and CO2 in some sort of a pattern to both sequester CO2 in the reservoir, as well as to help push oil and other hydrocarbons toward a production well. This, at least in the United States, doesn't give you as much of a tax credit, but it does give you a marketable product that fits in perhaps with the infrastructure that's already in your producing area. And so in many cases, CO2 is seen as sort of like that next EOR technology beyond perhaps a water flood. In this figure from the US DOE, I forgot to cite them here, but they're the ones that provided this. It shows CO2 being mixed with water to provide the right sort of control on moving that bank of oil toward a production well. So again, EOR is one strategy. It works in some places. The benefit of this is that there's a lot of characterization that's been done on oil and gas reservoirs. And so that data can help de-risk that reservoir with respect to CO2 storage. There's core analysis data, there's lots of well logs, lots of well penetrations in oil and gas reservoirs. Now, if we take a look at the other major method of CO2 storage, which is called saline storage, because we're storing it in a saltwater or brine horizon. Now, this can potentially provide storage in a lot of other places, right? We know that oil and gas reservoirs do not exist everywhere, but oftentimes we can assume that there's at least some sort of a brine permeated sedimentary formation under almost everywhere. These reservoirs can be more, like I said, more common geographically, but because there's no economic driver to penetrate these formations, there's a lot less data. And so from that respect, it's going to be more important to drill characterization wells, recover core samples, and characterize the quality of that reservoir and the seal over it. And I should say in the previous slide too, in this exercise, the reservoir is important, but the seal is also important, because one of the most important things you're going to need to show is that the CO2 stays in the reservoir, or that you can predict that it will stay in the reservoir long term. All right. Another form of storage that is less commonly talked about, but in some places around the world, this is the best kind of storage they have. It's called basalt storage and mineralization. And so this expands CCUS, or carbon storage, into rock types that aren't traditionally thought of as water-bearing, oil-bearing, gas-bearing stratigraphy. So basalt itself is highly porous. This is an igneous rock rich in iron and manganese. Places around the world that have a lot of basalt, like Hawaii or Iceland, Eastern Washington State in the United States, these are all places that have thought about storing CO2 in their basalts. And what's kind of interesting about this method of storage is that injected CO2 is modeled to react with the calcium that leaches out of the basalt through interaction with rainwater or other basinal waters, interacts with that calcium and mineralizes into calcite, or calcium carbonate. And so in this form of storage, we have not just storage of CO2, but actually conversion of that CO2 into a long-term durable mineral form that can be more, which is perceived to have less risk than storing as a plume in a reservoir in the subsurface. Now, basalt itself is not equally spread across the earth, just like oil and gas reservoirs aren't. And so this is a technology that's this is a storage theme that is gonna be more relevant in certain geological environments. Like I said, Iceland, Washington State, these are two places that have actually done, they've drilled characterization wells and done test injections of CO2 into basalt. This picture I'm showing here is from injection into basalt in Iceland. But they're trying to prove that technology up so that those areas can be potential zones for carbon sequestration. In addition to that, there's the Mid-Continent Rift that runs under the middle of the United States. There's tens of kilometers of basalt in that rift, and that's a place that could be explored for storage. There's also the mid-ocean ridges where we have fresh basalt coming out of the mantle that is highly porous. And by injecting CO2 into that sort of environment, it might be possible to there sequester CO2 far away from where the rest of the population lives, right? Also, there's large outcrops of basalt in India and the Deccan traps, as well as in Siberia, the Siberian traps. So there's basalt elsewhere, and so you shouldn't just think of carbon storage as being a sedimentary basin thing. There are lots of research groups out there going after this idea, this theme of storing it in basalt. There's enhanced mineral weathering, and so this is an interesting way that actually doesn't involve the use of a subsurface reservoir. In this case, it's almost close to being a carbon utilization technology, but essentially this is a way that you could turn or pull CO2 out of the atmosphere directly without having to capture it from some industrial emitter or a transportation emission source, just by using the CO2 in the atmosphere to weather minerals. And so when you weather something like crushed basalt or some ashes that are produced from various industrial activities, when you have this calcium silicate and you expose it to water at the Earth's surface, it will weather into silicic acid and a bicarbonate ion. Those ions then travel through runoff, through the soil column, surface waters toward the ocean, or they become lithified within the soil column to become a, again, durable mineral form of CO2 in the form of calcium carbonate or calcite. And that mineral weathering is a way to get rid of CO2 from the atmosphere. This is almost, this method of CO2 sequestration is interesting because it pulls in a whole nother industry that we don't talk about very much in oil and gas, and that's agriculture and mining. So like you would need to mine these minerals, you would need to process them to the right size, right? The higher the surface area, the faster the reaction rate. And this can allow the agricultural industry to participate in the idea of sequestering carbon out of the atmosphere. I'm going to move here toward talking a little bit about the risks of CO2 storage. I've touched on them, briefly throughout this presentation. But the big four risks for CO2 storage are: one, induced seismicity; two, a leakage of the brine from the storage reservoir into drinking water aquifers; third would be leakage of CO2 to the surface; and then finally the deterioration of abandoned wells, which sort of plays into the idea of leakage out of the storage reservoir. And so I'm going to go through these, and I'll say that these, by saying that they're risks, I'm not saying that they are inherently risky, right? That these are just, like all things in life, there's a risk to doing anything. And so we need to characterize, one, how risky these are toward any CO2 sequestration project, but also we need to characterize the relative risk. Is this riskier than having a chemical plant in my area? Is this riskier than driving my kids to school in the morning? Is this riskier than buying a lottery ticket? We can say things are risky, but we really also need to be able to communicate the relative risk of something so that people, so the general public, so that regulators, so that industry can characterize that risk compared to the risks they already take every day, right? We all take risks every day. We're all taking a risk right now watching this presentation when we could, be in a place where a meteor comes through our roof and intersects us at a high rate of speed. But we know that that risk is very low and it's probably negligible. So we need to be able to communicate our risks effectively. But in this section, I just want to communicate the risks that are there so that you can understand and think about start developing a model in your own head about what are the risks and how risky they might be. So the first is induced seismicity. This tends to be a very, how do I want to say this? This is a very hot button topic. This is something that the public knows a lot about and has strong feelings about induced seismicity because the public generally dislikes earthquakes. And their mental model of what an earthquake is has been primed on through a lot of Hollywood movies and you know, the recounts that we have from the terrible earthquakes that have affected this country along the coasts and here even in the middle part of a country, right? So we've had magnitude 9 earthquakes in California. We've had magnitude 8 earthquakes here in the center of the United States just from natural causes. Now the seismicity that tends to be induced from, say, geological operations of businesses are orders of magnitude, several orders of magnitude smaller, but in some cases, the induced seismicity from injecting wastewater, say down in Oklahoma, south of here, where I live in Kansas, is, you know, you can cause a magnitude 5 earthquake, and that's a pretty strong earthquake. It's enough to knock a chimney off the side of a house, right? So that's the sort of level of earthquake, and it's enough that can wake a person up. But we, you know, as geoscientists need to be able to communicate what the risks are for the certain injection scheme or injection pattern or injection plan that we have for a CO2 sequestration site. And this figure shows a number of different, you know, geological activities that can cause induced seismicity. Here, you know, it has a well here for CO2 sequestration, but it also talks about dams, mining, geothermal, shale gas, and hydrocarbon storage. The one thing this figure doesn't really show as well is, you know, with shale gas exploitation, we have the hydraulic fracturing that can cause, you know, or can induce seismicity, but also the disposal of wastewater from that operation, which often goes into other formations, that can also induce seismicity. But with CO2 sequestration, you know, because there are so few operations going on, we don't have good data, but more than likely, these are going to be really small events that are more than likely not going to be felt at the surface of the earth. All right, so abandoned wells. Abandoned wells are another issue with CO2 sequestration, like they are with all wastewater disposal or all waste disposal into wells, right? Around the world, we have a legacy of wells that are no longer in use for either water production, oil production, gas production, or other types of wells where those wells deteriorate with age. Some of them were not plugged and abandoned appropriately in the first place. Some have just undergone natural decay of their materials. And these wells, you know, penetrate stratigraphy and provide, you know, avenues for material to move up and down through stratigraphy against those natural permeability barriers that we have in the subsurface. And so one of the risks we have to characterize in every CO2 injection pattern is to think about where are the abandoned wells, how well are they cemented, how well are they going to keep materials from moving up and down the wellbore. This is again an issue that you know, there isn't as much recognition in the public about abandoned wells, but when they become an issue, they become an issue that's very serious. Now, what's really exciting is with the new technologies, again, coming out of, you know, the drone industry, we've got new sensors that are out there that are able to help characterize, you know, a potential CO2 storage area for its presence of abandoned wells, many of which are, you know, may not be recorded in official records. And so there's magnetometers that can be flown over sites. There's high resolution LiDAR scanners that can be flown to help find these older abandoned wells and be able to characterize, again, the risk with which those previous wellbores pose to future injection schemes. There can be aquifer impacts on oil and gas, or on from CO2 sequestration. So here we can see an injection well There's a gray plume down here for the supercritical CO2. But if there are faults that lead from that injection horizon upwards, that CO2 can leak into shallower drinking water reservoirs. Also, even if that fault doesn't intersect the CO2 plume, the pressure change from the injection of CO2 could force something like a brine into a shallower horizon. Now this is a risk with any sort of injection into the subsurface, and it's just a risk that needs to be characterized, modeled, and communicated effectively, and with respect to other risks that exist in both geological operations and other industries at the surface of the earth. Okay, so let's move towards utilization now. So algae, inorganic materials, working fluids, and fuels and chemicals are ways that we can utilize carbon that has been captured. And in many cases, these involve the capture of CO2 as well. So we're going to talk a little bit about capture here, a little bit about utilization. So while the center of this molecule that the DOE has put together is called carbon utilization, you see these 4 processes: uptake, conversion, services, and mineralization. And through the next 4 slides, I'll just give an example of each one of these. Okay, first, mineralization. Now, I talked briefly earlier about how we can mineralize CO2 through interaction with basalt, or through the weathering of basalt in, say, an agricultural field where we can draw that CO2 out of the atmosphere. One other major way to mineralize CO2 is through interaction with concrete. So during the production of cement, we actually drive CO2 off of calcium carbonate and emit it to the atmosphere. That's part of the process. And so actually cement production creates something like 5% of global CO2 emissions every year. Now what that does is that creates a deficit within the concrete for CO2. And over time, concrete actually carbonates and it absorbs CO2 out of the atmosphere. So one way that we can make cement production more carbon neutral is to enhance that rate at which concrete absorbs CO2. That can either be through action within an industrial facility, like, say, taking a precast concrete beam, putting it in a pressure chamber filled with CO2, and speeding up that process of carbonation, which also strengthens the beam. Or we could take something like a concrete road that is no longer in service because it's too cracked, it's no longer safe to drive on, and rather than, say, burying that concrete in the landfill, crushing it and leaving it exposed to the atmosphere to draw CO2 out of the atmosphere. And in fact, many jurisdictions will crush old concrete roads and use those as material to build gravel roads. And again, that increase in the surface area increases the reaction that pulls CO2 out of the atmosphere. But as you can see here, these are all ways to sort of, get CO2 into a solid form. And so mineralization is really that idea of taking CO2 from a gas, turning it into a mineral. We can also turn it into, we can use those precipitated carbonates as mineral fillers in things like paint. We can use them in, mineral additives to feed for livestock and things like that. All right, so moving on to uptake. So uptake is, how do we take that CO2 and put it into biomass, essentially? One of the major systems that's been proposed is taking the gas directly from a CO2 producer and feeding it into an algae system. In the case of this diagram that I show, or not diagram, this picture that I'm showing here, this is what's called an open algae system. So the algae is open to the atmosphere. And by injecting CO2 through the growth medium, those algae have plenty of CO2 to feed their photosynthetic activity. In this way, it's been seen that we can actually increase the production of biomass over just what would normally occur through diffusion of CO2 from the atmosphere into the growth medium for these algae. Companies like ExxonMobil are investigating this in terms of how they can create biofuels which actually don't require fossil hydrocarbons and can be more carbon neutral. But in this case, you have an open system. Some systems are closed, so that would be where the atmosphere that's interacting with this growth medium is controlled and at a higher partial pressure of CO2 than the surrounding natural atmosphere. Right. Next would be conversion. So conversion is the method of converting CO2 into some sort of a fuel or a chemical. And so in this case, we have, some sort of a cell, a chemical cell that has CO2 as one of its feedstocks, and then using various bacteria to convert that CO2 into, say, acetate, methane, hydrogen, some other usable fuel or chemical that would be beneficial to an industrial user. In terms of services, CO2 itself can be used as a working fluid. In that way, we're not creating or destroying or converting CO2. We're just running it through a system and using its chemical and physical properties in some way to, to support an engineering process. In this case, as I show here, it's being used as part of an enhanced geothermal system, whereby cool CO2 is injected down into a hot granite rock formation that's highly fractured. That CO2 picks up heat. The heat comes back to the surface and is exchanged into a geothermal power plant before returning back as part of a closed loop. In this case, a fixed volume of CO2 is being used. But if you have enough of these plants, then they become, a major use or a major user of CO2. All right, in terms of transport, three major ways to transport CO2: trucking, pipeline, and shipping. Pipelines are by far the most economical ways to transport any sort of gas or liquid. However, they are often the most contentious because they involve crossing people's property. Here I'll show you the pipelines that exist, at least in the United States, that run from a number of various CO2 sources, industrial CO2 sources, shown here in the purple squares. And in fact, they run from a number of natural CO2 reservoirs as well. You can see here Bravo Dome, Sheep Mountain, McElmo Dome. These are all places that have natural CO2-rich underground gas sources, and these have been used for enhanced oil production in a number of oil and gas fields around the country. Though the decline in production from these natural sources has also provided a natural driver for the connection of industrial CO2 sources to these CO2 pipelines, so that the EOR schemes that are running can still continue to run, but now instead of using natural CO2, using industrial sources of CO2. And you should also take away from this, there's quite a bit of controversy about whether CO2 can ever be stored underground, because doesn't everything in the subsurface leak? Well, we can look at these natural reservoirs that contain vast amounts of CO2 that have not leaked over geological time periods, millions of years, tens of millions of years. The Earth materials can store CO2 effectively for geologic amounts of time, because we have examples of this all over the world, not just in the United States. All right, pipelines, another pipeline that's under construction, it's called the Alberta Carbon Trunk Line up in Canada, and this is going to be the world's largest CO2 pipeline by amount of CO2 transported. When it's done, it'll be almost 15 million tons of CO2 per year, or equivalent to 2.6 million cars, at least Canadian cars. I guess if it was American cars, that'd be a little bit fewer. But this is going to be a big infrastructure project that then other both CO2 producers and CO2 users can plumb into to take advantage of. Here in the United States, Wyoming is considering connecting a series of pipelines together to make what they would call the Wyoming Pipeline Corridor. And this they see as a way to prolong their extractive oil and gas industry and their coal industry, which is where Wyoming gets 65% of their state level revenue. And so they're seeing this as a way to prolong the industries in their state, which are very carbon intensive. In terms of trucking, here in Kansas, for one of our DOE, Department of Energy funded research projects where we did a small scale pilot injection of CO2, our only option was to have the CO2 delivered by truck. And so that 33,000 tons of CO2 came, being pulled by truck after truck over the length of the injection. The CO2 had the same effect as if it were to come by a pipeline, but in this case, it came by truck, and so it was much more expensive. Very few, if any, CO2 storage schemes are envision using trucking, but it is a possibility that exists. In terms of shipping, in Europe, where there's a lot more coastline and a lot of industrial facilities are near that coast, there's this new plan that's been put together called Northern Lights, where in the first phase, they're planning to take CO2 from a recycling plant, an ammonia plant, and a cement factory and ship it 600 kilometers to an offshore reservoir for injection. This is a project that's being run by three heavy hitters in the European oil and gas industry, Shell, Total, and formerly Statoil, but now Equinor. But then in its final phase, it'll be even bigger, looking to inject 5 million tons per year from all around Europe into the same Northern Lights storage site. So I'd like to end this presentation by just again making some bigger statements about CCUS and how it can help us move forward as an industry, as a petroleum industry, toward being a carbon industry. So it's a new way of doing business that is different than how we do normal oil and gas. But in this change, there's opportunity to develop new technologies, opportunity to develop new relationships, opportunity to develop new businesses. And perhaps more than anything else, it's an opportunity to make a difference. There's not as much, I think in the oil and gas industry, we take a lot of pride in providing gas to people's cars, and we provide, these fuels for the global economy. But often we don't get a lot of slaps on the back. We don't get a lot of thank yous from people. But I think CCUS is a way that we can say, yeah, we're the oil and gas industry, but we're doing it right. We're making a difference, and we're solving this problem that's out there. And I'll just end with a quote from a former US president here. He said, "We choose to go to the moon." He said this about his challenge that we're going to land a person on the moon. He said, "We chose to go to the moon in this decade and do the other things, not because they're easy, but because they're hard." And certainly CCUS isn't easy because it's not well established, right? Nothing is easy when it starts. And I think we can do a lot as an industry and as geoscientists and geoengineers and business people to take our industry where it needs to go by developing the CCUS technology to its greatest extent. So with that, I'll just say, I invite you to register for my carbon capture, utilization, and storage course, where we'll talk more in depth about what I've talked about throughout this presentation. In the course, we'll talk, in more detailed fashion about all these different projects that are going on right now and how each project is intertwined with the geology of the area, with the economic landscape of the area, and with the government regulations of that area, so that you understand that each project isn't just operating by itself. It's actually part of a fabric of economic activity that's being promoted at various levels of industry and government. We'll also talk about those natural CO2 accumulations, so you can see, how does nature make an integrated CO2 storage system that doesn't leak, right? Because if we can see how nature does it, then maybe we can design design our storage systems just like nature does. And then finally, we'll talk, a lot more about the economics of CCUS so that you understand what is needed to make, to convince an investor to invest in your project. So with that, I'll say thank you.